So I want you to, if you have this file, look up the k-means clustering that we did. The thing is, I had some trouble uploading the videos, especially for the ones that are recorded on this computer because it's just slow and then sometimes it doesn't record at all. So maybe you don't have it. So in that case, I'll try to go slow in the beginning so you can follow me if you had to. Okay, but if you have the k-means clustering, let's save this as a different name. We're going to save this as random forest iris. Okay. All right. So let's execute some of the files. Import Seaborn as SNS because that's the graphing library we're going to use. And then we're going to use pandas as PD, sklearn datasets. And from the datasets, we're going to load up the iris datasets. And we put sFrame true so that we can define df as the iris.frame. So we can just use the pandas data frame because often this is more convenient. Let me just delete this one. Okay, so I need to define iris data frame, and then let's just do df.head to see if it was loaded up correctly. Get rid of that. Okay, so we're going to say df equals to iris.frame and df.head. We'll show you some of the data sets. Now the data sets appear in order. There are three varieties of iris, and the groups are number 0, 1, and 2. Zeros appear first, and then 1, and then 2. So that's why you see on the target is just 0. These are various lengths and widths of sepal and petal. And because I don't like to use sepal length parenthesis CM to talk about this column, I'm going to rename the columns as usual, df.columns, SL, SW, PL, PW, target. So that's done. And now we can use SNS Seaborn scatter plot. And we're going to scatter plot the data frame df with x coordinate being the sepal length, y coordinate being the sepal width, and the hue, depending on whether the target is 0 or 1 or 2, we're going to make it as the hue so that the three groups will have different colors. And I like the dark 2 color map, so let me use that one. And we will plot this. And here's the nice looking picture. Now, as you can see, it seems like this group here is somewhat well divided. The group 0 is well divided from the other two, but these are somewhat mixed, so this is not so good. On the other hand, if I plot using the petal length and width, which is the length of the flowering part, let's also use dark 2. And then you can see that in this direction it's less mixed. So over here there's some mixing. It will be quite challenging to do a linear separation. But even with some kind of a, let's say, a separation using kernel so that the decision boundary doesn't become a line but it becomes curved, I think you'll still have some trouble over here. Okay, so let's see if our PCA components will give us a better better direction where the two data sets are split better. Sometimes that helps. So let's do from sklearn decomposition import PCA, and we'll just take two components of PCA, and then we're going to make the PCA fit this data set. So now the new columns will be created because we've taken two PCA components, the principal component axis. So we'll use the first principal component and the second principal component added to our data frame. So if you so for example, if I let's put it in something. Let me add here. If I do df.head, now I see that the first two components are filled in with the PCA1 and PCA2 are filled in with the principal components. Any questions, or am I going too fast? Do you want to type something? It's okay. All right, so let's continue. Now let's try to use the two principal directions to see the picture. It's not any better. I mean, I can see that somewhere here may be a decision boundary, but it will still misclassify some stuff. Okay, but here's the idea. We're going to make decision trees and random forests now using all the four features, sepal length, sepal width, petal length, and petal width. Along with this PCA, we're going to add this to it as well. Maybe this might help as an additional one. All right. So let me. The rest of the code is k-means, so I'm going to delete all of these. So let me delete. Okay. Now let's add. All right. Now here comes the decision tree. So what I'm going to do is from sklearn, let's see, .tree, import decision tree, and then you can do tab completion. So let's tab, and it gives us two things. So you can use decision tree classifier, which does the classification. If you want to use decision trees to make predictions, then you use the decision tree regressor. So we're doing classification, so we're going to choose classifier. But for your finals project, if you're trying to use decision trees to predict numbers, then you can try the other one. All right, and then we are also going to import from the tree, scikit-learn tree, something called plot tree because I want to see the tree plotted as well. Okay, let's split my data into training set and split test set, sorry. So I should do that. So let's do that. From sklearn.model selection import train test split. In our previous code of the k-means clustering, k-means was an unsupervised algorithm, so it didn't need training or test. because we were assuming that the labels weren't there. So if you don't have any label, what can you train? But we are going to use the train test split available in scikit-learn. And we're going to say that train and test are train underscore other. Again, do tab completion. You may have to wait a little bit. Okay. Now it's done. Train test split, df, comma, and then we'll say test size is equal to, let's try something like 0.4, 40%. We're going to use, not test, 0.3, okay. So we'll use the test size as 0.3, which means we're going to use 70% of the data to train. Then train x equals to train. From the train, we're going to get the SL, SW, which one is it? PL, PW. These are the original feature sets that were given to us, but we've made the PCAs ourselves, so let's add that as well. There's PCA1 and PCA2. So that's going to be our train X, and then train Y would be the target variable, which is which group it is. So train target. Now let's copy this, copy these two lines, paste, and now we have to also do the same thing for test X and test Y. So I'm going to change this test Y, test. Oops. Okay, so now we have train and test sets split. With these, now I can train my classifier. So I'm going to say classifier is equal to decision. Again, do tab completion, tab, completed, and then decision tree classifier dot, and we're going to fit the train X and train Y. All right. Okay. So it's going to train. Okay. Now let's try to plot this. So plot tree CLF, and then we're going to say filled equals to true. If you don't have that set up, the tree comes out very small. So I'm going to do this. Okay, and here's what we have. Okay, this is our Genie. Okay, a few questions. How many leaf nodes do we have? Can you count? What's a leaf node? Huh?
13.
No, what is a leaf node? Yeah?
It's where the decision tree ends.
Ends, yeah, places where it ends. Now, this is not so good because all the arrows are not visible. There should be an arrow where the ones going left are the ones that are true, going right are false. So here's one leaf node. This doesn't lead to anywhere. Sorry, the arrows are so small. There's a small arrow sticking out here from here to there. So this is a leaf node. That's another one. That's another one. This one, this one, this one, this one, and this one. How many did we count? 8. Okay, so we have 8 leaf nodes. How many branching nodes do we have? Internal nodes do we have? So this is the very first one's called the root node. The other ones are internal nodes or branching nodes. So you have 1, there's another one, 2, 3, and then 4, and then 5, right? There's another one. Did I miss something?
Yeah, at the left.
Oh, there's another one here. Okay, yeah, 6. Okay, so there are six branching nodes, and then how many levels does this tree have? There's 1 level, 2 level, 3, and then there's 4, 5, 6 levels, right? 6 levels of decision. So the longest length a sample would go through to get a conclusion which tree it belongs would be 6. So we'll be going through 1, 2, 3, 4, 5, 6 criteria would be the longest criteria applied to get you to this one. Let me ask another question. What does this Gini equal to 0.0 mean? What does that mean? Gini equal to 0.0. We learned about this last time. Yeah?
Is that like that's like the type of group it is?
It's that's a little vague. Yes.
Yeah, there's a lot of entropy in the system.
No, it's actually the opposite. Yes.
It's the decision boundaries for each one, and
No, that's not what Gini is. So Gini is what's called the Gini impurity index. Okay. It tells you how impure your thing is. Okay. So once it reaches Gini equal to 0.0, that means it's completely pure. It only consists of one group. That's what it means. Okay? And you can see that every time it branches, right, you have 0.0, so there's no more need to branch off further. Over here is 0.49. So let's follow here. The Gini went from 0.665, went to 0.499, went to 0.139. But somehow over here it split off a pure group. And because it split off of a pure node, the Gini went up again because there's still some things to classify, right? And here it shoot off another pure one, but look at the sample size, it's only 2. So it really didn't affect it that much. In fact, before, out of the 40 samples, 33 was split into this part, so the Gini increased over here, but over here, you split out a very small sample, so that's why Gini became lower, because you've identified that some of the things that don't belong in this group, most of the group belong over here, so Gini goes down. So you can kind of see just by looking at the samples, if this side, if there's a pure node being output in a single branch, and the node that's produced has a bigger sample than the next branching node, then the Gini will actually increase. On the other hand, you can see from here and there the samples are smaller. Yeah, so I guess it's not always, but you can kind of see what's happening if you had the previous picture. And if you are to make a decision tree, you can kind of look at these Gini coefficients and make sense out of the numbers. Now you also notice that when this tree is plotted, there's a color, right? So at the very first branch, it has a strict boundary, which just simply says that if, what is this? This is petal length. If petal length is less than 2.45, it's definitely group 0. And there was no outliers at all. There was like clear boundary. So this just split off immediately. The decision tree, for the decision tree, this was really easy, so it just split it off. And then now you have mix of group 1 and 2. So you get this, and then once you split off huge amount of the green guys, right? Then this becomes more purple. So I guess I don't know which one's group 1 or group 2. Oh yeah. So let me see. Yeah, group 1. So the left says group 1. So the green guys are group 1. So this is colored green because there are more samples in this one that's green than purple. The purple group guys are group 2. This is colored purple because there are more guys that are purple than green. But at some point, the greens get taken out, and now you have more green, and then eventually it does this. Now, there's something more worrisome about this, the fact that some of these leaf nodes have only one sample. What does that tell me? That tells me that this decision tree is highly overfit. So I think it's not going to do a good job when you actually apply it to the test set. So let's try that. Let's see how well it did, right? So let's use from sklearn.metrics, import classification. Let's tab, see what's available. Might take a while for tab here. Oh, it didn't give me because I forgot an I, right? So classify, tab, okay, good. So classification report, and then we'll print classification, again, tab completion, oh, yeah, that one. And then we're going to use the test Y compared with the prediction of the classifier. So classifier clf.predict test X. Okay, so let's see what the report is. Wow! Accuracy 98? Really? Okay, that's hard to improve. Sometimes these things are very dependent upon the training and the test split. So let's do this. Let's go back and then let's run the train test split again, because I think we may have gotten lucky. Somehow the decision tree got a good sample which told them about everything. So let's see. Now you have a different tree because we fed in we chose a different training set. So this is what we got. Let's do the same classification. It's still 98%. Huh. Okay. That's all right. That's better than when I was trying it on my own. Okay. So that means even if I do the random forest, it's not going to really improve anything. But nonetheless, let me show you the random forest. Okay, so from sklearn.ensemble import random random forest classifier. That's the one that I want to pick. And CLF equals to random classifier. And then we'll use number of trees, number of estimators. Let's use 100 trees, okay? And then so I explained that there are two kinds of criteria that's used for decision trees and random forests. Those are Gini, which we already saw before, and the other one was the entropy. So this time, let's try entropy. Yeah, I don't like this because it's already at the decision tree level. It did such a superb job. There's no way I can improve that. But anyways, let me fit train X and then train Y. Okay, now shift enter. Okay, so we've fit using the train X and Y. Oh, I know why. When I was doing this alone, I wasn't using the PCA. The PCA 1 and 2 columns were added, and that allowed for the decision trees to do a better job. So that's something to, that's a nice lesson. So if you're doing your own project and if something doesn't work, then try to use some PCA into your thing. It can help. All right, so now let me copy from the previous one. Or was it? Oh yeah, this one. So let's just copy the classification report, paste it over here. Oh, 100%. Oh, wow. Okay, so it did improve. Wow, this is like my first getting 100 out of machine learning. All right, so yeah, good. So it tells us that indeed the random forest did improve over a single decision tree. So I explained what random forest is, right? It's a way to make many decision trees by doing bootstrapping, which means you just randomly select from your training set to make a new data set where repeated examples may be found. And then also you can, what else were we doing when doing random forest? Oh yeah, we were also using part of the feature sets. So instead of using all 6, we original data set had 4 feature sets, and we added 2 PCA components. So there were 6 feature sets, and the random forest was picking just only a part of the feature. Maybe it was picking 2 or 3. I don't know what the default is. All right. So let's try to see what the trees in the random forest look like. So we can still use the plot tree. And what we can do is we can do clf.estimators underscore. This underscore means in Python it's a way to say it's a private variable. Do not touch this from the outside. So we can still look at what it's in there, but an underscore is there so that other programmers using this don't mess with the variables directly. Okay. So let's look at the very first tree in the forest and see what it does. Okay, so the very first tree in the forest is this one. Oh, where did the colors go? That's strange. Okay, but anyways, here's the first tree. And then we can also go for the second tree. Yeah, wow, second tree is a lot more complicated than for the first one. All right. So you can see that there will be 100 trees in this forest using different criteria to make a judgment. And anytime they see a sample, all of the trees will start barking, right? They're going to say, oh, this is group 0 or 1 or 2, and the majority will take over and then give a single prediction. Okay? So that's the cool thing about random forest.